Hello everyone, in this video we're going to explore topic 10.11, finding Taylor polynomial approximations of functions. Alright, we're going to talk about the linear and quadratic approximation. Alright, so in topic 4.7 we know that the linear approximation is given by this formula. This guy actually the point slope formula which you learned from algebra 1, right? Y minus y1 equals m times s minus s1. So it's going to be y equals m times s minus s1 plus y1, right? So this one is y1, this one is m, this is s1, right? Now, this linear approximation is the first degree polynomial of s. So we can name this one as p sub 1 of s, right? So we replace L of s with p sub 1 of s, right? Now the problem is that linear approximations don't always work so well when the graph of f has a great deal of curvature near C. So then, in order to fix this problem, we're gonna create a quadratic approximation. Alright, so we just add a times s minus c squared. Right, this one is the first degree, this one the second degree, right? Now we need to solve for a, right? So here's the p2 of c where s equals c, right? So we substitute over here, we get f of c, right? Now we take the derivative of this one. So we derivative of f of c, this is a constant, it's gonna be 0, right? This is a constant, we just rewrite it, right? Derivative of s equals 1, right? A is a constant, we just rewrite it. Bring 2 to the front, we're going to use the power rule, so we get this one right here, right? Now we substitute c for s, right? So we're going to end up with this guy right here, right? Now we're going to check the second derivative, so it turns out to be 2a only, right? This one is 0, right? So P2 double prime of C where S equals C equals 2A, right? And you know that P2 double prime of C is the same thing as F double prime of C equals 2A. Divide both sides by 2. We get this one right here. So we substitute this guy back to the formula right here and we get this one right here, right? Now example number 1. Find the linear approximation to f of s equals ln s at s equals 1. Right, so we have p1 of s equals f of c plus f prime of c times s minus c. Right, f of s equals ln of s, and it's going to be p1 of s, right, equals f of c, so it could be ln of c plus derivative of this one is going to be 1 over s, right? So it could be 1 over c, right? Because s equals c times s minus c, right? This one is c equals 1. So we have ln of s is ln of 1, right, plus 1 over 1, right, times s minus 1, right? Ln of 1 is equal 0, right? So this one equal s minus 1, ln of s, right? Now question B, find the quadratic approximation to this one, right? So we need to find p sub 2 of s. It's going to be f of c plus f prime of c times s minus c plus 1/2 f double prime of c times s minus c squared, right? We have ln of s is the same thing as p2 of s, and it's gonna be f of c, which means ln of c, right, plus 1 over c, right, s minus c plus 1/2 f double prime. So we have f prime of s equal 1 over s f double prime of s equals negative 1 over s squared, right? So you have times negative 1 over c squared, right? Times s minus c altogether squared, right? Now you have s equals 1, which means c equals 1, right? So substitute 1 for c. So you have ln of s equals ln of c, which means ln of 1, right? Plus 1 over 1 times s minus 1. Subtract 1 over 2, right? Times s minus 1 altogether squared, right? Now we're gonna simplify, so it be ln of s equal, this one equals 0, right? It's gonna be s minus 1 over 2 s minus 1 altogether squared, right? Now question C, use these approximations to estimate the value of ln of 1.05, right? Now we have P1 of 1.05 is gonna be this guy right here, right? 1.05 subtract 1, right? So it could be 0.05. Now we're going to use P2 of 1.05. It's going to be right here, right? So it could be 1.05 minus 1 subtract 1 half times 1.05 minus 1 altogether square, right? So it's going to be 0.05 minus 1 half of 0.05 square, right? So we're going to print up the calculator, right? So it's going to be 0.4875, right? Now the next question, how do these approximations compare to the actual value of this one? Alright, so we're going to print up the calculator to find the actual value, right? So we're going to press Control E to the S right here, right? Put 1.05, press Control Enter. It's going to be 0.04879, right? And you see that P2 gives you the answer that's closer to the actual value, right? So P2 approximates the function better than P1, right? So the higher degree polynomials, the better, right? We're going to move on to the Taylor polynomials. So if you proceed the same process, you're going to end up with this formula right here. We have definition of n Taylor polynomial and n Maclaurin polynomial. Alright, if the function f has n derivatives as c, then the polynomial is given by this formula. Is called the n Taylor polynomial of the function f centered at c, and this guy right here is called the coefficient of the n degree term in a Taylor polynomial. Similarly, now if c equals 0, substitute 0 for c, you're going to end up with f of 0, f prime of 0 times s minus 0, which means s, right? F double prime of 0 over 2 factorial s minus 0 square is going to be s squared, right? And then the n terms right here is called the n Maclaurin polynomial for the function f, and this one right here is called the coefficient of the n degree term in a Maclaurin polynomial, right? Note that Maclaurin polynomial is a special case of the n Taylor polynomial, right? Now let's move on to example number 2. Maclaurin polynomial for the sine s. Now find the 7th degree Maclaurin polynomial P7 of s for the function f of s equals sine s, right? Now we have f of s equals sine s, right? And then we can calculate f prime of s equals cosine s, right? And then f double prime of s equals negative sine s. Then f triple prime of s equals negative cosine s. And then the fourth derivative sine s, right? And the fifth derivative is going to be cosine s. The sixth derivative is gonna be negative sine s, right? And the last one, the seventh derivative, is gonna be negative cosine s, right? Now, since this one is Maclaurin series, right? So we're gonna substitute 0 for c, right? So we have f of 0 equals sine of 0 is gonna be 0, right? F prime of 0 is gonna be cosine of 0 equals 1, right? F double prime of 0 is gonna be negative sine of 0 equals 0. F triple prime of 0 is gonna be negative 1, right? Now this one equals 0, right? The fifth derivative of this one, s0 is gonna be 1. The sixth derivative is gonna be 0. And the seventh derivative is gonna be negative 1, right? So we have the formula P7 of S equals f of 0 plus f prime of 0 times s, right? Plus f double prime of 0 over 2 factorial s squared, right? Plus f triple prime of 0 over 3 factorial s cubed plus the fourth derivative of 0 over 4 factorial s to the 4 plus. Now we just substitute values, right? F of 0 equals 0 right here, right? F prime of 0 equals 1, so we have P7 of S equals S, right? F double prime of 0 equals 0, so this guy gone, right? This guy gone. F triple prime of 0 equals negative 1, right? So we have negative 1 over 3 factorial S cubed, right? This guy right here equals 0, right? So it's gone. The fifth derivative is going to be 1 right here, right? So you have plus 1 over 5 factorial s to the fifth, right? The sixth derivative equals 0 right here, gone. The seventh derivative is going to be negative 1, right? So minus 1 over 7 factorial s to the 7, right? Now, if this one is the f of q, you just leave it like this, right? But you need to simplify if this one is the MCQ, right? So you have s minus 3 factorial is going to be 3 times 2 times 1, right? So it's going to be 1 over 6 s cubed, right? 5 factorial is going to be 5 times 4 times 3 times 2 times 1, right? So it could be plus 1 over 120 s to the fifth, right? Minus 7 factorial is going to be 1 over 5, 0, 4, 0, s to the 7, right? Now question B. Use P7 of s to approximate this one, right? So we have P7 of 0.2 is going to be 0.2 minus 1 over 6 times 0.2 cubed plus 1 over 120 times 0.2 to the fifth minus 1 over 5040 times 0.2 to the 7, right? So we're going to print up the calculator, press Ctrl Enter. It's going to be 1.9869, right? Now question C. What do you notice about the degree of each term of P7S? So we see that the degree of each term is 3, 5, 7, which is odd, right? Since the sine function is odd, right? Now, can you make an assumption about the degree of any Maclaurin polynomial for the cosine s, right? So similarly, the degree of each term is even for cosine s, since the cosine function is even, right? Now let's move on to example number 3. A function f(s) is differentiable for all orders and has the following derivative values when s equals 1. Right? Use the third degree Taylor polynomial for f(s), center s equals 1 to approximate this one, right? So we have p3 of s equals f of c plus f prime of c s minus c plus f double prime of c over 2 factorial s minus c square plus f triple prime of c over 3 factorial times s minus c cube. We stop right here, right? Because it's a third degree, right? Now we substitute 1 for c, right? So we have p3 of s equals f of 1. F of 1 is 2 right here, right? Plus f prime of 1. F prime of 1 equals negative 3 times s minus 1, right? F double prime of c is going to be right here. So it's going to be 1 over 2 factorial. It's going to be 2, right? Times s minus 1 square plus f triple prime of c is going to be right here. Negative 6, right? Negative 6 over 3 factorial is going to be 6, right? Times s minus 1 cube, right? Now we're going to simplify this one, so it could be, now we need to approximate this one, right? So f of 1.1 is the same thing as p of 1.1, right? So it's going to be 2 minus 3 times 1.1 subtract 1 plus 1.1 subtract 1 square over 2 minus 1.1 subtract 1 cube, right? So we're gonna print up the calculator. Control Enter. The answer is. Now let's move on to example number 4. We need to find the coefficients of the Taylor and Maclaurin polynomials. Alright, question A. Let f be a function with third derivative f triple prime of s equals 7s plus 2 to the 3.5. What is the coefficient of s minus 2 to the 4 in the 4th degree Taylor polynomial for the function f about s equals 2? We're given f triple prime of s equals 7s plus 2 to the 3.5, right? So we need to find the 4th derivative of s, right? It could be 3.5 times 7s plus 2, 3.5 subtract 1, it could be 1/2, right? And then times derivative of 7s plus 2, it could be 7, right? So it's going to be 21 over 2 times square root of 7s plus 2, right? We have f4 of 2, right? Center at 2 equals 21 over 2 square root of 7 times 2 plus 2, right? So 7 times 2 could be 14 plus 2, 16 square root of 16 equals 4, 4 divided by 2, it could be 2, 2 times 21, it could be 42, right? So remember the general terms of the Taylor polynomial is given by the formula f n of c times s minus c to the n over n factorial, right? Now this coefficient is this guy right here, right? So we have f4 of c equals 2, right? Over 4 factorial, right? So f4 of 2 is going to be 42 right here, right? So 42 divided by 4 factorial, it could be 24, right? So we're going to divide the top bottom by 6, so it could be 7 over 4. Now question B. A function f has a Maclaurin series given by this guy. And the series converges to f of s for all real numbers s. If g is the function defined by g of s equals this guy, what is the coefficient of s in the Maclaurin series for g? Alright, so remember Maclaurin series center s equals 0, right? Now we have the Taylor polynomial for this guy. It's going to be p and of s equals, so we have the Maclaurin series, which means c equals 0, right? So we have p and of s equals. Now we need to take the derivative of this one, so we have g prime of s equals, we're going to use the power rule, right? And then we're going to use the chain rule, right? So it's going to be f prime of s times e to the f of s, right? So we have g prime of 0 is going to be f prime of 0 times e to the f of 0, right? Now f prime of 0 is the function f of s right here, right? F prime of 0 is the coefficient in front of s, so it can be right here, equal 4, right? Now times e to the f of 0, this one is the constant in the function f of s, it could be right here, right? So it could be 3, right? Now the question wants us to find the coefficient of s in the Maclaurin series. Coefficient of s in the Maclaurin series is right here, right? Look, s right here. So g prime of 0 equals 4 times e to the third. So this one is the final answer, right? Now example number 5, a function g of s has derivatives of all orders at s equals 0. It's known that g of 0 equals 2, g prime of 0 equals -1, and the general term is right here for n greater than or equal to 2. Find a third degree Maclaurin polynomial for the function g of s, right? This is very simple. So we have p3, right? Third degree of s equals g of 0 plus g prime of 0, right? Times s plus g double prime of 0 over 2 factorial times s square plus g triple prime of 0 over 3 factorial times s cubed, right? Now we just substitute value. So g of 0 equals 2 plus g prime of 0 equals -1, right? So I have negative s right here, right? G double prime of 0 equals this formula right here, right? So it could be plus 2 square, right? Over 2 factorial, right? And then you have 2 factorial, so you just rewrite this one, right? And then times s square plus this guy is going to be 3 square over 3 factorial times 3 factorial s cubed, right? So we're going to simplify this one, so it's going to be 2 minus s plus 2 factorial is going to be 2, this is going to be 2, and then cancel out this one, so it could be s squared, right? 3 factorial is going to be 6, 3 factorial is going to be 6, this is going to be 9, right? So 9 over 36 is going to be 1 over 4 s cubed, right? Now let's move on to example number 6. It's going to be similar to example number 5, right? The only thing different right here is the function g of s given by the integral of this guy, right? So you just take derivative of g prime of s equals bring s over here, right? F of s. G double prime of s equals f prime of s, right? And g triple prime of s equals f double prime of s, right? We can stop right here, right? Because this is third degree Taylor polynomial, right? Now we need to calculate g prime of 0 equals f of 0, right? F of 0 equals 4. G double prime of 0 equals f prime of 0 is going to be -3. and g triple prime of 0 equals f double prime of 0 is going to be 3, right? So we have the third degree Taylor polynomial for g about s equals 0, so it could be Maclaurin series, right? So p3 of s equals, now we plug in values, g of 0 is going to be this guy right here, g of 0 equal integral from 0 to 0 f of t dt. This guy and this guy the same, the answer must be 0, right? So this one equals 0. G prime of 0 equal 4 right here, right? So you have 4s. G double prime of 0 equal negative 3, right? So minus 3 over 2 factorial equals 2s squared, right? G triple prime of 0 equals 3 right here, right? So plus 3 over 3 factorial equals 6, right? So 3 over 6 could be 1/2, right? S cubed. Now let's move on to example number 7. Consider the logistic differential equation dy over dt equals y over 6 times 4 minus y. Let y equals f of t be the particular solution to the differential equation with f of 0 equals 6, which means t equals 0, y equals 6, right? Question A. Write the second degree Taylor polynomial for f about t equals 0, right? So this guy actually Maclaurin polynomial, right? So we have the formula b2 of t equals f of 0 plus f prime of 0 times t plus f double prime of 0 over 2 factorial times t squared, right? Now f of 0 is 6 given right here, right? Now f prime of 0 is this guy right here, right? dy over dt when t equals 0, right? And y equals 6, right? So substitute over here, you have 6 divided by 6, it could be 1, right? 4 minus 6, it could be negative 2, right? Now f double prime of 0 equals d square y over dt square at t equals 0, y equals 6, right? So we're going to take the derivative of this one. So it could be, we need to expand this one first, right? So we have 4 divided by 6 could be 2 over 3y, right? Minus 1 over 6y squared, right? So it could be 2/3 y prime, which means dy over dt, right? Minus, bring 2 to the front, it's going to be 1/3, right? Y, and then dy over dt, right? So then we substitute 0 for t, 6 for y, and negative 2 for dy over dt, right? So we have 2 over 3 times negative 2 minus 1 over 3 times 6 times negative 2, right? We're going to simplify, it's going to be negative 4 over 3 plus 4, right? So it's going to be 8 over 3. Alright, so we substitute into this formula. So we have p2 of t equals f of 0 equals 6 right here. F prime of 0 equals negative 2, so subtract 2t, right? And f double prime of 0 equals a over 3, right? And then divide by 2, it could be 8 over 6, which is 4 over 3, right? So plus 4 over 3t squared, right? Now question B, use the results from part A to approximate f of 1, right? So f of 1 equals p2 of 1, right? So it could be 6 minus 2 times 1 plus 4 over 3 times 1 squared, right? This could be 16 over 3, right? Now let's move on to the last example, example number 8. The position of a particle moving along a straight line is modeled by s of t. Selected values s prime of t is shown in the table above, and the position of the particle at time t equals 10 is s of 10 equals 8. Question A. Approximate s the program of 8 using the average rate of change of s prime of t over the interval for 10. Now you know that 8 is between 4 and 10, right? So s the program of 8 equals s of 10 subtract s of 4 over 10 minus 4, right? So it could be 4 minus 5.8 over 6, right? So it could be negative 1.8 over 6. It could be negative 0.3, right? Now, question B. Use the correct units. Explain the meaning of s the program of 8 in the context of the problem. So we need to say that the rate of change of the position of the particle is decreasing by 0.3 meters per second at time t equal 8 seconds. Now question C. Use a right Riemann sum with two subintervals to approximate the interval from 0 to 10 absolute value of s prime of t dt, right? So basically we just calculate the error, right? Now we need to find the width, right? From 0 to 4 the width is 4, from 4 to 10 the width is 6, right? Now the height, since this one is the right Riemann sum, right? So the height is right here, 5.8 and 4, right? So you have the width times the height, so 4 times 5.8 plus 6 times 4, right? So it could be 47.2. Now question D. Let s be a function such that the third derivative of s with respect to t is this one, right? So we have s triple prime of t equals t minus 3 to the 7. Write the 4-degree term of the 4-degree Taylor polynomial for s about t equals 1, right? So we need the 4-degree terms, right? So we have the general term is going to be, now we need to find s4 of t, right? So it's going to be 7 times t minus 3 power of 6, right? We need to take the derivative of this one, right? So s4 of 1, right? Because t equals 1 right here. It's going to be 7 times 1 minus 3 power of 6, right? So it could be 7 times negative 2 power of 6, right? So we're going to print up the calculator. 7 times 2 power of 6. The answer is 448, right? So we're going to substitute into this formula right here, right? So we have the 4-degree term is f4 of c times s minus c to the 4 over 4 factorial, right? Now c in this situation is 1 right here, right? So we have f4 of 1 is going to be 448, right? So we have 448 times t minus 1 to the 4 over 4 factorial. Now we need to simplify, so it could be 448 times t minus 1 to the 4 over 24. So it could be, divide the top bottom by 8. So it could be 56 over 3 times t minus 1 to the 4, right? Now, one of the primary goals of studying Taylor polynomials, and later in topic 10.14, Taylor series is to find a way to represent an ugly function as a prettier function that we can manipulate much easier. Alright, so we look at this one right here. This one is ugly function, and it's gonna be prettier function right here, right? And it's good time to stop. Thank you for watching. I hope you enjoyed the video. Remember that if you failing to prepare, you're preparing to fail.
We rise like tall buildings as the chemicals they take us higher. The night's young and it's just begun as she puts her hand